Oh,
I'm just testing.
uh, uh,
Yeah,
are you hearing?
it's working.
Okay.
Focus in the back.
Okay.
Yeah.
Thank you.
Great.
Good morning, everyone. I'm Jang Min Park from Yeongnam University, South Korea. And this is my first time to visit this conference. And my talk is about the Phoenix application to solve two-phase flow problem. And I use Can-Hilliard model to describe the interface between the two phase. And some particular thing about this work is that the interface has not only the surface tension, but also it has viscosity. And there is something special about this work. And this is the outline. First, we'll talk about the interface first and some mathematical equations, and then some results on the convergence test, and some results on toy problem, droplet in the shear flow. And the interface, when we have two immiscible fluids, the interface is created between two fluids. And for instance, when we have water and oil or water and air, we have interface between them. And when we don't have any molecules or particles on the interface, we say the interface is clean or interface is simple. And for that such a simple interface, we have surface tension only as a stress on the surface. And that is described by that equation. But when we have some molecules or particles on the interface, then we have some complex structure on the interface, and we say that surface or the interface is complex interface. And with that complex interface, we have extra stress with the red term there. There is extra surface stress during the deformation of the surface. And there are many kinds of different constituted laws for that stress. And in this study, we only consider a viscous interface model or the Buzynski scribe model as shown here. And in that equation, we have shear viscosity and dilatational viscosity of the interface. And we are going to use that model to see the effect of viscosity on the deformation of the interface. And when we want to describe the deformation or when we want to describe the interface, we have two different approaches. One way is to assume the interface as a surface, and that is called sharp interface method. And across the interface, we introduce a boundary condition as a stress jump condition, which looks like this. Across the inner and outer fluid, across the interface, we have stress jump condition. And yeah, the surface stress consists of two parts. The first one is from the surface tension, and the second part is extra stress. And for the sharp interface, we have different approaches to capture the interface or to track the interface. We may explicitly track the interface in a Lagrangian way, that is called interface tracking method, or we may use some scalar function to implicitly describe the interface position. And anyway, they are the sharp interface approaches. And as I mentioned, the surface stress is introduced as a boundary condition on the surface interface. But in this study, we want to use diffuse interface, which is based on the Can-Hilliard model. And in this case, the interface is not just not a surface, but it is a thin, narrow region. And everything is continuous in this model. So the surface stress can be introduced as not as a boundary condition, but into the momentum equation. That's one advantage of this approach. And we don't suffer from singularity issue when we have morphology change of the interface. But to capture the high gradient of the solution across this interface, we have to have very fine mesh across the interface. But anyway, we are going to use this diffuse interface model due to many advantages. And this is a Stokes Canhillier system. As you already know, we have tutorial, Phoenix tutorial for Canhillier system, Canhillier equation, and we also have Stokes equation tutorial, Phoenix tutorial. And here, because we solve this, we couple this Canhillier with this Stokes equation, we have convective term inside here. And in the Stokes equation, we have a capillary stress here. And okay, and this is the original Stokes-Canhillier equation, Stokes-Canhillier system. And because we want to add the viscous stress of the interface, we add that term into the momentum equation like this. And this formulation was presented about 10 years ago, but they use sharp interface method. So this term was eventually treated as a surface integral. But in this work, we do not change anything because we use continuous diffuse interface model. So this Dirac delta function can be defined as a magnitude of the gradient of phase field. Anyway, every equation is now ready, and we have finite element formulation, almost the same as the Phoenix tutorial. And we use a second order interpolation for C and mu, and P2, P1 for velocity and pressure. And we use second order time integration for the Canhillier equation. And we first do some convergence tests. So we produce manufactured solution for the Canhillier equation first. So we add this G term. So the phase field is just convective problem. So we can find the analytical solution easily for given this initial condition. If we apply shear flow, the solution looks like this. With that given analytical solution, if we calculate the capillary stress or the surface extra stress, that we can find that they do not contribute, they don't have any contribution to the momentum balance equation. So the flow field also can be analytically given in this by this simple shear flow equation. So anyway, we have manufactured solutions. So we have convergence tests, and these are the results. So we can see the third order convergence for C and mu as expected, to the L2 errors, and second order convergence for H1 error of mu, U velocity, and second order on L2 error of pressure. So also we check the convergence of time integration, the second order convergence of L2 errors in C and mu. And as I mentioned, we have high gradient of solutions, so we need a very fine mesh near the interface. So I use the remeshing refinement function in Phoenix to locally refine the mesh at the interface, depending on the gradient of the phase field at each time step. And this graph on the right side shows the error depending on the number of local refinement. Zero refinement means the uniform mesh, and as we increase the number of refinements at the interface, we get convergence as before. And now we apply that system to solve some toy problem like drumlet in the shear flow. On the boundary, the flow field is given, and we fix one point, the pressure of one point is 0. And this is the other boundary conditions for the Canhillier equations. And with that toy problem, I want to compare the result between the diffuse interface model and the sharp interface model. And these are the result comparison between the diffusion interface on the upper figures, and the lower is the sharp interface model. The sharp interface model is the result is not from the Phoenix, but I use the TFM software library developed by Martin Hulsen from TU Eindhoven. And anyway, this is the pressure field. This sharp interface model uses Lagrangian interface tracking, and this diffuse interface model, as I mentioned, we use local adaptive mesh refinement. We can see I will show the graph soon, but anyway, we see the agreement. This is for the viscous interface. We also see they match well. So if I plot the pressure along the diagonal of the domain, you can see the sharp and diffusion interfaces result match very well. The only difference is that with the diffusion interface, we have continuous change of the pressure across the interface, as shown in here, where the sharp interface, we have this continuous jump of the pressure as expected. And this is a velocity field also to show the agreement between the diffuse interface and sharp interface method. And finally, I have applied it to a larger deformation problem to show the effect of surface viscosity. And with the surface viscosity, the drumlet tend to have smaller deformation than with the simple interface. Anyway, this work is ongoing, and this is the end of the result. So in summary, we have developed a Cahn-Hilliard-Stokes system to solve the two-phase flow problem with the viscous interface, and we applied adaptive mesh refinement and have studied some convergence and drumlet deformation. And actually, many things are ongoing, mostly to extend this model to 3D problems. And we may introduce different kind of constitutive models like elastic or viscoelastic interfaces. And I hope to show the results maybe next Phoenix conference. And finally, I want to acknowledge the financial support and TFM libraries from Martin Hulsen. And I also want to thank all these Phoenix community members. And thank you for listening.